Is it linked in yet?
No,
I didn't even look at the clock. I'm gonna assume that it has been. And say that we are jumping now into section 3.6. So section 3.6 is all about this idea of vertical asymptotes and infinite limits. So let's say we've got, it'll be easier to show. Notice when we approach in this particular function 3 over x minus 2. When we approach 2 from the right and when we approach it from the left, we approach infinities. So one-sided limits here, they do in fact exist, but not the limit as a whole, right? Here we're saying from the right, we go to infinity, from the left, we go to negative infinity, but the limit itself does not exist because it doesn't agree. This is what's called a vertical asymptote. This is what form, or this is how they're formed. If there's a value x equal to c, and your function coming at it from the left and from the right approaches some sort of an infinity, then you've got a vertical asymptote. And notice it doesn't have to be from the left and the right, it's or. So we could have a situation like this. I've never seen it, but we could have it. Your function does this and would still call that value a vertical asymptote. Like I said, I had never seen this actually show up in anything, but it theoretically could. I take that back, I have seen this before. In my undergrad research I did. So all you need is one of those limits from the left or the right to go to infinity. But only if it's at x equal to c, right? Only if it's in the limit as x approaches c. Then you say at c, there is a vertical asymptote. So that's a bunch of examples. Limits from the left that go to, a bunch of different values. We've got from the left, a goes to negative infinity, and from the right goes to infinity. Corresponds with this graph here. Oh, they do have, sweet. Notice here, we go from the left up to infinity, and from the right down to negative infinity. Notice they could actually agree as well on which infinity they go to. We could have both sides going to negative infinity, or both sides going to infinity, and it's still a vertical asymptote. All you need is one side going to infinity, the end. Just one side going to one of the infinities. That is literally pretty much everything there is to know about vertical asymptotes insofar as what we're concerned with. But some things can happen when we put in particular functions, right? Like, so for example, what I mean is, in this function here, x squared minus 2x being in the denominator forces two different possible discontinuities. We can factor out that x squared, oh, they already did that below, cool. We can factor out that x squared minus 2x as such, and get these two different zeros. One at x equal to 0, and the other at x equal to 2. So there are two different x values that our function would be discontinuous at when x is equal to 0 and when x is equal to 2. difference just because our denominator could be 0 at either one of those values. So that forces two different asymptotes. One at 0, one at 2. As we approach 2 from the right, we go to infinity. As we approach 2 from the left, we go to negative infinity. As we approach 0 from the left, we go to infinity. As we approach 0 from the right, we go to negative infinity. So we've got two asymptotes. But because the asymptote at 0 is along our y-axis, we don't draw it in. We could, if we wanted to, we could be pedantic and draw like this. And extend the dots representing our asymptotes outside of our graph. We could be pedantic and do like that, but generally we don't. If there's an asymptote on one of your axes, we usually leave it as it is. Usually. Just say, all right, I can't really do much about it. But it is a good idea when working on your own to write it down just so you know it's there. Now, what about something like this? Where are our vertical asymptotes here? Should be at 2 and negative 2, right? Because x squared minus 4 can be factored into the quantity x plus 2 and the quantity x minus 2. So we have x plus 2 times x minus 2. And that's all in the denominator. So 2 and negative 2 should be asymptotes. Oh, wait. 2's not. Why not? What's happening? Get your numerator really quick. Your numerator, in this particular case.
Because if you put 2 squared plus 2 times 2, that's 4. They add up to 8, so make it 0.
I think you're on the right track. I didn't quite catch what you were saying, but let me write this down. What were you saying?
So if you plug in 2 for x, 4 minus 4 is 0 on the bottom, right? And then 4 up top plus 2 times 2
Right.
is 4. So.
Well, what I'm asking is, okay, so we can factor this.
Yeah.
This comes out to be x squared plus 2x minus 8 divided by, like you just pointed out, our numerator can be factored, or I mean our denominator can be factored. So in theory, we've got two places where there should be an asymptote. Why isn't there an asymptote here? It's because our numerator can also be factored. Our numerator can be factored as the quantity x minus 4 times the quantity, my mistake, x plus 4 times the quantity x minus 2 divided by the quantity x minus 2 times x plus 2. So what's happening is that we have this factor that can kind of be canceled, right? X minus 2. And when that happens, we get that this thing is equal to x plus 4 over x plus 2 whenever x is not equal to 2. Because we removed one of the zeros in the numerator. So we have to denote it here. And that's why instead of having two asymptotes, we only have one and this whole. It's because one of those possible asymptotes was able to be factored out. Is everybody cool with this? Notice the possible asymptote that we couldn't factor out at x equal to -2, that's the one that became an asymptote. I mean the discontinuity, I should say, at x equal -2 is the one that remained to become an asymptote. So because we were able to factor out one of those discontinuities, that discontinuity became a whole. The one that remained became an asymptote. Took out that x minus 2. So it's simplified to this expression everywhere except at x equal to 2. And this thing has a discontinuity at x minus 2. That's what this asymptote is. And just comparing solutions, lo and behold, they point out the same thing. This thing is continuous everywhere except at x negative, or x is equal to -2. So we have to say, all right, yeah, don't include x equal to 2. That forces that whole. And that's what's happening. Cool? So, another type of limit, something that we haven't really quite talked about yet. What happens if we actually want to go to infinity or to negative infinity? Let's take, for example, the limit as x goes to infinity of 1 over x. What is that equal to? Well, as you divide by larger and larger values, you get out smaller and smaller inputs, right? Things that are closer and closer to 0. If you could do that forever, divide by larger and larger values, you would only get closer and closer to 0. It doesn't matter if those large values were positive or if they were large in the sense of very large negatives, right? Just larger values in general. As they got larger, you got closer to 0. The limit, as x approaches infinity of 1 over x, then thing's got to go to 0. And only Chuck Norris can prove it, because he's the only man who can count to infinity and beyond. No, really? No Chuck Norris joke? God. Man, I should charge y'all for my comedic relief. Oh wait, the school already does, I guess. All right, so what does it mean to have a horizontal asymptote? It's a logical question followed by, since we just talked about vertical asymptotes, a horizontal asymptote is what happens when you take your limits to infinities and negative infinities. If your limit comes out to be a number, that means you have a horizontal asymptote. So notice 1 over x. We actually have both a vertical and a horizontal asymptote. They just happen to be along our axes. So 1 over x, it has two different asymptotes, a vertical one and a horizontal one. And when you go out, when you take your limit to infinity, you get 0. Okay, that confirms one of those vertical or one of those horizontal asymptotes. When you take it out to negative infinity, still gets 0. That confirms that our horizontal asymptote is just 0, right? But just like you could have multiple vertical asymptotes, you could have multiple horizontal asymptotes. It doesn't have to be the case that going to infinity agrees with going to negative infinity. So, as an example, we've got something like the arc tangent. Going to negative infinity, this thing might go to 1, to negative 1, and going to infinity, it might go to 1. That's what arctan would do. Well, actually goes to negative pi over 2 and pi over 2. Right? Yeah. Negative pi over 2 to pi over 2. Similarly, you may just have a limit on one side of your function. You may not go to a number as you approach negative infinity or positive infinity. But the reverse case might happen. So what I'm saying is you might only have an asymptote in one direction. Which, unlike the band, is kind of cool. I think I'm funny and clever. I don't even care. So another example of some asymptotes that we might find. A horizontal asymptote like this. Notice what's happening with this. Compare this x squared, compare the idea of 1 over x squared to 1 over x. 1 over x squared, even if you put negative values in, it's going to give you out positive values. So 1 over x squared, that thing is going to look like this. So when we subtract 1 over x squared from anything, we get the reflection. Multiplying it by 2, well, that just stretches it. And adding 5, well, that just raises it. Which is why our graph comes out to be this kind of tornado funnel looking thing. And the way we can find this horizontal limit is we can take the limit out to infinity, and we can take the limit out to negative infinity, find that they agree. Oh, this thing goes to 0, so all that's left is 5, and in both directions we go to 5. Then we can say, all right, well, what happens when we go to 0? When x goes to 0, well, our function then goes to negative infinity. So we have a vertical asymptote as well. Is everybody cool with this? Dope. All right. Now, there's some tricks to this. These are really just here to help us navigate different forms. These are really, honestly, just tricks, observations that'll help us. So if the degree, I don't want to read these directly off to y'all because y'all can read them yourselves, and everybody hates the instructor that just reads the slides. So I'm going to jump to the problems. And we're going to work through these one by one. All right. in this first problem, notice the degree of our numerator is less than the degree of our denominator. If the degree of the numerator is less than the degree of the the operator is less than the degree of the denominator, then y equal to 0 is going to be one of our horizontal asymptotes. Now think about why this is happening. When we take the limit as x goes to infinity, this 2x term is going to be dominated by this 2x, this 3x squared term, right? This thing is growing a lot faster than this thing is shrinking. So in that way, the growth of our denominator is going to outpace the growth of our numerator, and that's why we know that y is going to be equal to 0, or that we have a horizontal asymptote at y equal to 0. Is everybody cool with that? Similarly, if the degrees are equal, you're going to need to check out the coefficients. That's what's happening in this case. We have -2, we have 3, all right? So given that the coefficient, the leading coefficient in our numerator is -2, and the leading coefficient in our denominator is 3, we're going to find that we have a horizontal asymptote at -2/3. And that's just because they don't really outpace each other, actually. They kind of agree. But there is a tug of war that's happening. You do have your numerator tugging down and your denominator tugging up. And where they agree, where they hit a sort of equilibrium, is going to be that -2/3. This is occurring because the numerator and the denominator are of the same degree, but with different leading coefficients. If they have the same leading coefficient, dope, it's 1. And then finally, this last case, your numerator has a higher degree than your denominator, so there is no horizontal asymptote. Why is that? Well, it's because your denominator is growing less quickly than your numerator is. So your numerator can go to infinity far quicker than your denominator can. As a result, you can possibly get to infinity and negative infinity before your denominator does. So you can get a number out there, right? And keep getting numbers, keep getting numbers, and keep getting numbers forever. So you can grow or shrink accordingly as much as you want. Hence, you have no horizontal asymptote. Does this make sense to everyone? The intuitive idea of what's happening. So check it out. We've got, in our first example, the 3x squared and the 2x. We have our horizontal asymptote. One is at 0. Happens that they're both at 0, right? Why is that? Well, that's because this denominator is going to outpace over time your numerator. So as you get closer and closer to infinity, this thing gets big much faster than this thing. So bada bing, bada boom, you go to 0. Again, because these two things agree, it becomes a tug of war, and they have to go to whatever the ratio of the leading coefficient is. And this numerator happens to be bigger than this denominator. So in both directions, you can go as big as you want. Notice something interesting happens here. There is an asymptote. It's just not a vertical or a horizontal asymptote. You have an asymptote that happens to be this diagonal line. So chugging along, we get this idea. All right, this takes some time, what we're about to do. If there's anything up to this point with the concavity, differentiability, relative extrema that you feel rocky on, these are the sections that they correspond to. If you feel like you need to brush up on these, because these are going to be important to some of what we're about to do. We are now going to find the graph of a function just by looking at the derivatives of it. Starting with this beautiful x cubed plus 3x squared minus 9x plus 5. All right. First thing we want to do is what?
Find the derivative.
Yes, awesome. Thank you. I was really hoping for the quiet stoicism, but you are correct. Yeah. First, we're going to take the derivative of this thing, right? Our function, f of x, is equal to x cubed plus 3x squared minus 9x plus 5. So the derivative of this thing, well, it's just going to be f prime of x is equal to 3x squared plus 6x plus 9.
Would it be plus 9 or negative 9?
Good catch. Minus 9. Can't rush perfection. And we can factor out a 3 here, right? Let's factor out that 3. When we do, we get x squared plus 2x minus 3. Well, this thing can be factored. It can be factored as x minus 3, my mistake, x plus 3, and x minus 1. So automatically, we know our critical numbers just from this. Agreed? Critical numbers are going to be -3 and 1. So when f prime of x is equal to 0, that happens at x equal to -3 and x equal to 1. Okay. So, working all this out, -3, 1, that means our first interval is -infinity to -3. Our second interval is -3 to 1. And our third interval is 1 to infinity. God, I am really fighting that urge to be like, to infinity and beyond. No. Now we're going to pick some numbers inside of each of those intervals. I'm going to say let's go with 0 in this middle interval. Whenever you can, that's usually a good number.
Can we do the 0? Oh, sorry, never mind.
The middle interval. In the far left interval, I'm going to say let's go with 4. -4, I mean. And in the far right interval, I'm going to say let's go with 2. So what we're going to have then is 3 times -1 times -5, right? Because all we're doing is plugging in -4 into our first derivative. So that's going to come out to be 15. Plugging in 0, we're going to get 3 times negative 1. It's negative 6, or I mean negative 9. And at 2, we're going to get 3 times 5 times 1, so 15 again, right? That primed at 2 is equal to 15. So we are increasing, decreasing, increasing. All right, now part 2. Part 2, we're going to say we've got our first derivative was equal to 3x squared plus 6x minus 9. So our second derivative is equal to 6x plus 6, which we can factor. Pull out that 6, get x plus 1. So f double primed of x equal to 0 implies x is equal to negative 1. Right? So now,
Those are the possible inflection points, is that correct?
yes. So now, I'm going to break up our number line. At negative 1, this is going to be negative infinity to negative 1, and negative 1 to infinity. I say let's go with negative 2 and 2.
Sure.
Or negative 2 and 0. That would be nice too, right? Let's go with negative 2 and 0. X is equal to negative 2. X is equal to 0. When x is equal to negative 2, we have negative 2 plus 1, that's negative 1, times 6 is equal to negative 6. When x is equal to 0, we have 1 times 6, that's 6. So, are we concaved up or are we concaved down? And where?
Concave down on the left, concave up on the right, or flip flop?
I'm going to say, let's go with what you think. Concave down, concave up. I'm going to say, let's come back over here and see if this makes sense. We know we go from increasing to decreasing, but then from decreasing to increasing. So does it make sense that we might be concave up and concave down? Or I mean concave down and then concave up. Since we're going from increasing to decreasing, we're going to have that cup facing down, right?
Mm-hmm.
And since we're going from decreasing to increasing, we're going to have that cup facing up, right? Now, let's start graphing some of this. First, let's start by plotting where our critical numbers are. Then, let's come over here and look at where our possible inflection points are. Which, for the sake of delineating between the sets, I'm using squiggles for our second derivatives, right? Now, we know, so let me write it up here. X is equal to -1. Now we know, to the left of this, we are increasing. Through here, we're decreasing. And to the right of 1, we are increasing again, right? And we know that to the left of our squiggle line, we're concave down, and to the right of it, we're concave up. Now let's come back to our original function. Are there any values that might help us plot this? I say there is. Let's put in 0 for x. We get 5 out, right? So somewhere up here, let's start at 0, 5. Now we could go ahead and find where our function is equal to 0. So that's a little overkill, I think, right now. Because starting here, we already know some things. We know that we have at 1, a min, and at -3, a max. So let's plug in 1. 1 plus 3 minus 9. 1 plus 3 is 4, minus 9 is 5. 5. All right, we're at 0. Cool. So we're going to have our ball looking something like that. Now at -3, we're going to have 27 plus 27, so that's 54, minus 9 times 3 is 27 again, so we're back at 27, plus 5 is going to be 32, right? So we're somewhere way the hell up here. So our function is going to look something like this. Oh, I need to use another color because now we can't see anything. All right. So we said at 1, our function is equal to 0, and at -3, it was equal to, oh, my mistake, I did that wrong. This should be -27, this should be 27, those cancel, this should be -27 plus 5 is going to give us 22, -22.
Yeah.
So I made a mistake there. But
That's supposed to be going down.
you're right. Oh, because it's -9 times -3 is 27. So that was a typo in my head. These two cancel each other. This becomes 27 plus 5.
32.
Right. So we're increasing up to that. We have kind of a bowl shape here. Got kind of a bowl shape here because we're decreasing, increasing, and we know we're a min, right? We know we have to go through 0 here. Let's find out what happens at -1 now. Plugging in -1, we get -1. Plugging in 1, we're going to get 3. minus 9 times -1 is going to be -9. So just add the 9 plus 5. This is going to come out to be 3 plus 9 is 12, plus 5, 17, minus 1 is 16. We're somewhere around here-ish, right? And this thing is kind of an inflection point. So it does something, oh my God, this is horrible. It does something like this. All right, we're gonna pretend like my drawing is much, much better than what it actually is. We're gonna jump to the next slide to see that they did the same thing, right? They have where their critical values are and where their points of inflection could be. They checked whether we're increasing or decreasing and whether we're concave up or concave down. Looking at it, they then checked each of those points to find out where they were. They had their point of inflection at -1. They have their min, they have their max, and then they have another 0, which is just to say that you have another x-intercept here. So setting y equal to 0, we get this other point. And lo and behold, we were able to graph this function just by looking at the derivatives of it. Thank God, because otherwise we're going to have to check every possible point that we could and try to get a dense collection of points and hope that nothing crazy happened in between. So why do this? Well, we do this because there are some graphs that just aren't easy to get x, y values for. Let me show you what I mean. Stop share. Share grapher. 3D graph, 2D. Like that.
Oh.
Yeah. Imagine having to find a bunch of points to graph this thing. Zooming in, this thing isn't actually a constant block like it looks like. It's just that the numbers get so close to each other until you can't distinguish them apart anymore graphically. So if you were going to use a table to try and figure out what all of your different x, y values are, you wouldn't really be able to, because look at what happens down here around -0.032 up to 0.032. Once we get in this range, look how close all of these values are. You're going to need a giant, stupidly large table to find all of your possible x, y values and then plot them. And in fact, what ends up happening is at x equal to 0, you have a solid line from 1 to -1, because your function doesn't know where it wants to go. It goes to 1 and it goes to -1. And it goes to every value in between. So we have cases like this that we just wouldn't be able to plot by hand, just looking at points. But we can make that problem easier on ourselves by doing some of this. Granted, this method won't be able to plot this graph, but as an example of a graph that you cannot physically figure out using a table, this is one. That's why we have this method. Does that make sense to everyone? Oh, man, the Zoom didn't show it. Let me stop share. Let me go back to that. There we go. This is the graph I'm talking about. Like I said, as you zoom in, you can't tell the difference between one value or another. So physically by hand using a table, you can't plot this. You wouldn't be able to plot it with this method either, quite honestly, but it's because of things like this that we do have the method that we just talked about. Having said all that, it is 1 minute after, so I will let y'all go. Have a good day, everybody.